Okay, so some of these are going to be, you have to figure out the activity, right? We have to do a little, we're going to have to do a little chemistry here, right? But really just kind of the easiest possible chemistry, right? Okay, so the first thing I want to do, basically our activity is just lambda n. So we got to figure out lambda, we got to figure out n, and then we're done, right? Here's our half-life is 14 hours, right? So let's figure out the lambda. Half-life is the time it takes to reduce us to a half of what we have left, right? So if this is the half-life, we would just say 1/2 n naught is n naught minus lambda, and then this would be the half-life, right? Okay, and then of course the n naughts go the way of the bison, and we end up with ln of 1/2 is e to the minus lambda t 1/2, right? And then ln2 is, oh, whoops, the e goes away, sorry. ln2 is lambda times t 1/2. And then ultimately lambda is, you could just memorize this, couldn't you, right? t 1/2, right? All right, so let's see, my lambda is ln2. These should just give us that formula, which I'm kind of irked that they don't. So I'm going to go 14 hours. This has to be in per second probability. So I'm going to go 14 times 3600. All right, so ln2 divided by parentheses 14 times 3600. And that is 1.375 times 10 to the minus fifth, and that's probability per second, right? Same units as a becquerel, but different idea, right? All right, so now, now I'm going to plug this in here. Oh, we got to figure out n. We have to figure out n. All right, so how do we figure out n? We only have a small space to do it. Okay, let's see, we have that many grams. That's how many grams there are for a mole. And then we have to look up Avogadro's number, right? So n is number of moles times Avogadro's number, right? And number of moles is 0.0240 grams divided by, and then that's the grams per mole, right? So 39.964, right? And you can look that up in your little isotopic reference. I think I'll probably give them to you here, but there it is, right? Again, I don't know, let's see. Because I haven't decided that. I haven't actually written those yet. Okay, so 6.02. If I don't give them to you, you can just look them up. Yes. All right, 6.02 times 10 to the 23rd. And this is what, atoms per mole. Okay. Let's figure that out. Okay, so 0.024 divided by 39.964 times 6.02 e to the 23rd. That's a lot of atoms. I'm getting 3.615 E20 atoms. All right, so now we're all set. So we're just going to multiply this number 1.375 times 10 to the minus fifth probability per second, right? Per atom per second, right? Times 3.615, this number I just got here, right? Okay, times 10 to the 20th, right? And this is atoms, and we'll get our activity. Okay, so this guy times this guy. Well, that's a lot of activity. I'm getting 4.972 times 10 to the 15th counts per second. That's pretty cool, isn't it? Now, how would you ever measure that many counts per second? That's kind of a lot, right? Well, that's, here's the sample, right? That's what's going out of this sample in all directions, right? So you put your detector some distance away, you know what solid angle it subtends, And then you also know what the efficiency of that counter is, and you can figure this out, right? All right, good enough.